In this question, you started by asking for your things you've learned from your bookwork. When can a Poisson be used to approximate a binomial? And it's when you've got a large number of n and a small probability of it happening. Basic standard stuff comes up quite regularly for this one marker. But then we've got a hypothesis test. And the hypothesis test, it's known that it normally produces bolts with defective ones 0.03. So H0 is always P equals, and it's 0.03 here. And let's read through. Has it got better or has it got worse? They think it's got worse. They think the proportion of the defective bolts is higher. So it's higher, so greater than 0.03. So we've got a one-tail test, and it's a 5% test. So we're aiming for a 0.05 if we do this. Now, under H0, X, which is the number of defective bolts, I've not written that down, but I should do. It's a binomial. How many are they doing? 200. And the probability 0.03. But because that's a large number and that's a small number, we could actually say that can be approximated by a Poisson, times those two things together gives us 6. So we're looking at a Poisson mean of 6. Clearly, if you've got 6, then this is probably right. If we've got a lot more than 6, maybe we'd be going here. And the evidence was that actually there were 12 defective bolts. It does seem quite a lot, doesn't it? So we're going to go for 12 or more because we want to go more here. So we've got a lower end of 12, an upper end of 99999, and a mean of 6. And the probability of that happening is 0.02. That is pretty special, about 2%. So 0.02 is less than 0.05. We're in the special bit here. We are special. So we will actually reject H0. And reading the words again. So at 5%, there is evidence that proportion of defective bolts has increased. Context, the proportion of defective bolts has increased because we're suggesting it's here, not there.